Okay, welcome to our Thinking Beyond. Before we get started for tonight's webinar, I of course have my usual announcements. And first is just that our next Thinking Beyond will be the same last Monday of the month, which is February 23rd. I will send out the announcements with the speaker and the registration link mid-February, so you can look out for that. And then I'm very excited to announce our Beyond annual lecture speaker is Peter Turchin. And for those who are in town, it will be on March 31st at 7 o'clock. And the title is Our Age of Discord, A History of Possible Futures. So you can look out for registration links for that in the next coming weeks as well. For tonight's webinar, if you have questions at any time during the presentation, please use the Q&A feature at the bottom of your screen, and we will get to those towards the end of the hour. And so with that, I will just turn it over to Maulik Parikh, and he is the moderator for tonight's Thinking Beyond.
Thank you, Jessica. I'm Maulik Parikh. As many of you know, I'm at the Beyond Center for Fundamental Concepts in Science at Arizona State and theoretical physicist. And so I'd like to welcome all of you to this evening's Thinking Beyond, the first of our spring semester. And today we're very fortunate to have Professor Matt Kleban. Matt is a friend of mine, works on similar things, and he's the chair currently of the Department of Physics at NYU, at New York University, where he explores cosmology, elementary particle physics, and string theory. And his research focuses on the quantum physics of black holes and the origin and ultimate fate of the universe. As a boy, he read Stephen Hawking's Brief History of Time, and that inspired him to study theoretical physics to try to understand space-time and everything. His scientific contributions include pioneering work on black hole singularities, the subtleties of late-time cosmology, and the effects of cosmic bubble collisions, which I think we'll be hearing about today. I can say personally that I've read many of his papers from beginning to end, which is not how I usually read physics papers. So I'm very excited they're full of ideas, and I'm very excited to hear what he has to say today. The title of his talk is From the Quantum World to the Multiverse. With that, let me hand it to Professor Matt Kleban.
Thank you very much.
Wait, but just let me say one thing. And again, to reiterate what Jessica said, please type in your questions in the chat, and then we'll get to them afterwards. All right.
Thank you so much, Maulik, for that kind introduction and for the opportunity. And it's a pleasure to speak to all of you. Let me share my presentation here. So I'll be telling you about the idea of the multiverse and how it's connected to quantum mechanics. As Maulik said, I'm a professor at New York University. I'm here in my office. There's a lot of snow outside, and it's very, very cold. And I'm a member of something called the Center for Cosmology and Particle Physics, which was founded by a number of people who came from the ex-Soviet Union. So this was our logo, which Maulik was just enjoying. In any case, I wanted to start just situating us where we are in the universe. So our sun is part of a galaxy that we call the Milky Way. The Milky Way is a spiral galaxy. On the right here, if you can see my cursor, is an image of a nearby galaxy called Andromeda. And if we could somehow zoom outside of our own galaxy, the Milky Way, and look at it from a distance, it would look more or less like this. It's round, it's flat, shaped like a pancake or a plate. And our sun, our solar system, is situated somewhere near the edge, not all the way on the edge, but near the edge of this pancake. So maybe somewhere over here, if we were part of Andromeda. Now, I don't know how many of you are in Arizona, actually, but if you are, or you spend time there, if you go outside on a clear, dark night, someplace where there's not a lot of light pollution from cities, and you look up at the sky, you'll see something like this image on the left. You'll see a streak, a kind of a cloudy streak across the sky. It's called the Milky Way because it looks something like clouds of milk. And what you're seeing when you look at that is our galaxy. So if you imagine yourself situated over here in Andromeda, if you were to look towards the center of the galaxy or anywhere in the plane of that spiral disk galaxy that you're part of, you would see a lot of stars because you're looking through the bulk of that galaxy where most of the stars are. But if you look vertically up or down, you'll see a lot fewer. And so that's exactly what this image here is, or what you'll see if you go out at night. You see here the disk of our galaxy. And to the left and to the right of it, you're looking out of the disk, up or down, where there are fewer stars. So each of these galaxies has hundreds of billions of stars in it, as Carl Sagan used to say, billions and billions, right? So hundreds of billions of stars. For each person on Earth, 40 or 50 stars. So that's pretty good. But that's just in our galaxy. There are a lot more galaxies in our universe. This is an image from the James Webb Space Telescope, our most advanced space telescope, the successor to the Hubble Space Telescope. And if you look at this image, this is a tiny part of the sky, just very, very magnified. And you'll see, if you look around, many other galaxies. So there's one here, there's one over here, there's one over here. There are many galaxies in this image. There are also some nearby stars. This very bright object here in the middle is a star that's relatively close. And these straight lines are artifacts from the way the telescope is constructed. That's diffraction off the edges of the mirrors or the supports that are holding them. So this is just a nearby star, but you see behind it all of these galaxies. There's also something interesting that you can notice in this. This is a very special part of the sky because there's a massive object between us and these galaxies far away. And the gravitational pull of that object is causing gravitational lensing. It's distorting the shapes of some of these distant galaxies. So you'll notice these kind of stretched out features here. Those are gravitationally lensed galaxies. In any case, if you were to look around in every direction and count or estimate the number of galaxies in the observable universe, you'd count about 100 billion. So I don't know, what would that be? 15 or so galaxies per person on Earth. So if you weren't happy with your 45 stars, you can have 15 galaxies. And those galaxies, those are clumps of stars arranged in these disks or sometimes in egg-shaped regions. The galaxies themselves are clumped into regions called clusters and those into regions called superclusters. And our best model of all of this, of where it all came from, is that all of this structure, all these stars, all these galaxies, these clusters, et cetera, all of them were seeded in the very early universe by quantum mechanics. So according to the standard model of cosmology, the mainstream view, everything that you see in this image, and indeed everything you see when you walk outside and look up at the night sky, is quantum mechanics or was seeded by quantum mechanics. And those tiny quantum fluctuations in the early universe grew and grew and grew and eventually turned into all of the structure that we see today. So you can think of this picture as quantum mechanics processed through billions of years and magnified enormously. But quantum mechanics in the early universe did more or could have done more than just create these small fluctuations, more than just plant these seeds for galaxies. Depending on the theory, quantum mechanics can produce much larger fluctuations, which can generate not just stars and galaxies in the part of the universe we can see, but enormous regions that are isolated from the rest of the universe or nearly isolated and very far away. And if that's the case, then everything that we can observe is only a tiny fraction of this much larger structure, this full universe, which can be almost unimaginably diverse and enormous. And that goes by the name of the multiverse. It's not necessarily an accurate term. In some sense, the universe means everything there is. And so there can't really be anything beyond the universe. But the idea is that there's an observable part of the universe. That's what we've been describing with stars and galaxies. And anything beyond that, we're going to call the multiverse. So in this talk, I'm going to try to give you a sense of why we think the multiverse might exist. If it does exist, how we could test it or even rule it out. And what would it mean for us, for our place, if in fact the multiverse exists and we confirm its existence. So to explain a little bit of this, I first have to tell you a few things about physics and how it affects what we can observe. So I'm sure you all know that light does not move instantly. It doesn't transport instantaneously from one place to another. It moves at a very rapid, a very fast, but finite speed, which is about 186,000 miles every second. That means that in 1 year, light travels about 6 trillion miles. Um, to give you a sense, so when we call that distance, the distance that light travels in 1 year, we call it 1 light year. So to give you a sense of scale, our galaxy is roughly 50,000 light years across. So light from a distant star in our galaxy takes about 50,000 years to reach us. And the observable universe that has 100 billion galaxies in it is roughly 14 billion light years across. One of the interesting facts about this is that the further away you look, the further back in time you're seeing. So if you imagine listening to a fireworks display, let's say you closed your eyes and you just listened to the sound of fireworks exploding, you're hearing those explosions a few seconds after they happen. So when you hear a bang, it's an explosion that happened a few seconds ago, depending on how far away the explosion was from you, because it takes sound that long to propagate from the explosion to your ears. Now, even if you're watching these fireworks, it still takes a tiny amount of time for light to come from the explosion to your eye, but it's such a small amount of time since light moves so quickly that we don't ordinarily notice it. But if we start talking about astrophysical distances, then that delay, the time it takes for light to arrive, begins to matter. So for instance, the light we see from the sun, or if you were to look at the sun, you'd be seeing it as it was about 8 minutes ago, because the sun is about 8 light minutes away from us. When we look at distant galaxies, like the ones in that image I showed you, we're seeing them as they were hundreds of millions or even billions of years ago. And the most distant signals we can see originated almost 14 billion years ago, when the universe was very young, in a sense that we'll come to, about 400,000 years old. So that's young relative to 14 billion. I think it's worth pausing at this point just to point out that 14 billion years is obviously a very long time, but it's not actually that long compared to, for example, the age of the Earth, which is 4 or 5 billion years old, or the age of the sun. So actually, the universe hasn't been around that much longer than the Earth or the sun that we live on. About a century ago, a little more than a century ago, Albert Einstein discovered a theory of gravity, which he called general relativity. And his theory revolutionized the way we think about space and time, because according to that theory, space and time are dynamical. They're not rigid, fixed structures. And space can expand and change shape as time passes. One of the predictions of that theory is that a universe that contains matter and radiation, like the one we live in, cannot be static, which had been one of the prevailing theories of the universe prior to this. The universe could not be static according to general relativity. It would have to either expand or contract. And what does it mean for the universe to expand for space to expand in this theory? It means that if you have a universe full of galaxies, like illustrated here with these balloons, the space between the galaxies expands with time. Some people, when they hear this, they think, well, if everything expands equally, what difference does it make? And indeed, that would be true. If everything expanded in exactly the same way, including everything down to the atoms in your body and your brain, and everything is expanding, that's just a rescaling. It doesn't really mean a whole lot. That's not what happens, though, when, according to Einstein's theory, when the universe expands. Gravitationally bound structures like galaxies do not expand because their own gravity is stronger than this tendency for everything to grow. What does expand is the space between the galaxies. And so you see in this picture, the galaxies remain the same size, but the space between them grows and grows and grows. And if you're an observer living in one of these galaxies and you're looking around, you'll see all these other galaxies receding away from you as if they're all running away as fast as they can and directly away from you. But you'd see that no matter where you were on this balloon. That's one of the interesting features. There's no special point here. Now, if the universe is expanding as time passes, then if we run the clock back, if we go back in time, then everything is contracting instead of expanding. As the universe expands, it cools. And so as it contracts, going back in time, it heats up. The density of matter, the temperature, energy density, all of these things increase as you go back in time. And if you keep going back and you keep extrapolating the predictions of Einstein's theory further back in time, you come to a point where the universe is so hot and so dense that hydrogen, that's the most common element in the universe, a proton and an electron, hydrogen ionizes, as does everything else. Electrons are stripped off of protons, and matter is in a state called plasma, which you can imagine as being like the interior of the sun. So it's extremely hot, it's full of light. There are electrons and protons bouncing off each other and moving around very rapidly. Um, going back to that time, if you could somehow transport yourself back then, you would be, well, wouldn't be very healthy, but the universe would be full of this plasma. It would be extremely hot, full of light everywhere. And then going forward in time just a little bit, as the universe expands, it cools off, electrons are captured by protons and turn into neutral hydrogen. And much like the air in the room you're sitting in, that is very transparent. So there's this epoch in the early universe where the universe goes from opaque, full of plasma, to transparent, full of gas and neutral gas, just similar to air. And all the light that was filling this plasma, it didn't just disappear when this happened. It was all still there. All of those photons and light rays are moving around in different directions. And all of a sudden, the universe is transparent and there's nothing to absorb them or scatter them anymore. And that ancient light is still all around us. If you'd been around back then, you could have seen it with your eyes. It was visible light. But because the universe has expanded so much since then, that electromagnetic radiation, that visible light, was stretched out to a wavelength that's in the microwave spectrum. So there are now microwaves filling our universe, which are remnants of this extremely early phase in the history of the universe. And that's called the cosmic microwave background. When that was first observed, it was thought to be some kind of interference or static, but it's now understood to be perhaps the most important signal of the very early universe. It's the most ancient light, the most ancient signal really that we can detect. And it's been very carefully studied. There have been multiple satellites devoted to mapping out tiny fluctuations in that microwave background, because those tiny fluctuations are those seeds that I was mentioning before. Those are the seeds for the formation of structure. So here, there are some images here of the intensity or temperature associated with those microwaves at different points on the sky. So if we tried to see further back in time or further away than this point, we wouldn't be able to, because as I mentioned, this plasma that filled the early universe, like the interior of the sun, is opaque. If you were to shine a laser pointer on the sun, it wouldn't come out the other side. It would be absorbed at the surface. And so these cosmic microwaves, this cosmic microwave background, that's the earliest light that we can see. And since it's the earliest, it was emitted at the earliest time, that corresponds to the furthest away, the most distant object, if you want to think of it that way, or the most distant thing that we can possibly observe. So there's a maximum distance. And since this was 14 billion light years ago, sweeping a few details under the rug, it's about 14 billion years ago, it's about 14 billion light years away, this surface. And so that's referred to as a horizon. It's analogous in some ways to the horizon that you would see if you were on an island like this one. So you can imagine that you are an inhabitant of this remote island in some ocean far away. This green on the island, these are bushes, there are no trees. You have no wood to build boats. So all you can do is climb to the highest point on your island and look around. And when you do that, you see ocean and sky meeting. You see a horizon. You cannot see beyond that. But you might notice that when you climb to the highest point, you're seeing further than when you were a little lower down. And you could build a tower if you had some materials, maybe out of rock or something, on top of one of these peaks, and then you'd see even a little further away. And it would be pretty unreasonable for you to think that the world just ends at the furthest point that you can possibly see from the highest point on this island. I think it's equally unreasonable to think that our universe ends 14 billion light years away at the edge of the observable universe. The fact that we can't see beyond that is a limitation that we have to live with. It's not anything intrinsic about the universe we live in. And it would be very strange indeed if we were to draw a giant sphere of radius 14 billion light years around us, and we were at the exact center, and there's nothing beyond that. So surely there's more to the universe than the observable part. There must be more to the universe that we simply can't see, or at least not directly. And in a sense, positing that there's more to the universe than what we can see directly, is the simplest kind of multiverse. It says that there's a part of the universe that we think is there, but it's either unobservable or very difficult to observe. If we did try to keep going back, so we have a theory, even if we can't observe it directly, we do have a theory. We have Einstein's theory of general relativity, and we understand plasmas and a lot about that sort of physics. So we can keep running the clock back further to see what happens. The plasma gets hotter and hotter and denser and denser. And if nothing changes, if we can use Einstein's equations all the way back, or if we continue to use them, the plasma reaches a point of infinite density and temperature called a singularity about 400,000 years before this time that I was talking about, where it becomes transparent. And that is what's known as the Big Bang singularity. No one believes that there is truly a singularity, truly a point of infinite density and temperature. I think we all suspect that there's a theory that replaces Einstein's theory, that Einstein's theory is very accurate in today's universe, and it's very accurate in the early universe, but at some point, as you keep winding the clock back, it breaks down. One of the things that's missing from Einstein's theory is quantum mechanics. And quantum effects become very strong when densities and temperatures become very high. There is a quantum version of Einstein's theory of gravity called string theory. And according to string theory, which I'm not going to describe in any detail, but according to string theory, many of the laws of physics that we believe we understand, so for instance, the laws of chemistry, actually, not quite physics, but let's say the periodic table of the elements, that structure arises from properties of electrons and protons and neutrons. The laws of physics that govern those particles, their masses, their charges, their spins, those rules or laws would change depending on which phase of string theory you happen to find yourself in. So the particles that make up matter, the forces that act between them, something called the vacuum energy that I'll come to in a moment, and even the number of large dimensions of space can vary as you move around in this landscape of phases of string theory. So I mentioned the vacuum energy. This is one of the quantities that varies from phase to phase. Einstein's theory predicts that all forms of matter and energy gravitate, that all of them generate a gravitational field of some sort. And so even if you have a vacuum, an empty space, but it has a non-zero energy density for some reason, that energy density has an effect, according to Einstein. And empty space does appear to have an energy density for more than one reason. In string theory, one reason is that there are extra dimensions that are not necessarily visible, and there are analogs of electric and magnetic fields around which themselves have energy and give energy to empty space. But also, apart from string theory, just due to quantum mechanics, whatever types of particles you have around, quantum mechanics doesn't let them not exist at all. So you try to make space perfectly empty, and you'll discover that there are electrons and positrons and protons and antiprotons popping in and out of the vacuum, even though you tried to completely empty the space of anything. And those quantum fluctuations give rise to a vacuum energy. According to Einstein, once you have that vacuum energy, gravity will act on it. And if the vacuum energy is positive, it causes the space to expand, and not just grow, but expand at an accelerating rate, at an exponential rate, in fact, if that's the only form of energy around, so that in some amount of time, a given area or a given volume will double in size, and then in that same amount of time, it'll double again, and so on. And this is sometimes called inflation, not the financial sort, but cosmic inflation. So if string theory is correct, we have many of these different phases with different vacuum energies. And these phases can nucleate, they can appear. If you have a glass of champagne or a glass of beer, you have two phases. There's the liquid phase and there's a gas phase. And bubbles of the gas will spontaneously appear inside the glass. And once they appear, they'll rise to the surface. The analog of that in this theory is that bubbles of another phase will appear, and depending on the vacuum energy inside, those bubbles may recollapse and disappear, or they may start to grow and expand and grow faster and faster and accelerate outwards. It turns out that the inside of a bubble like that, a bubble that grows, contains a universe. And it's a universe which looks a lot like the one we live in. As far as you can tell from the inside, it's infinitely big. You won't ever see an edge. And it looks homogeneous. It looks more or less the same everywhere. And it looks isotropic. It looks the same in all directions. And the appearance of one of those bubbles is the Big Bang. It's not a singularity. It's a quantum event where a bubble appears. I won't try to explain the mathematics on this slide for you, but it illustrates how these bubbles grow and grow. The edges of them move away at a speed that approaches the speed of light, which is why you can never see them or catch up with them. And this explains how the universe inside one of these bubbles can appear to be infinite and homogeneous and isotropic to someone who lives inside one. If this were the right theory of the universe we live in, our universe would have certain characteristic features. It would have what's known as negative spatial curvature. And the spectrum of fluctuations on the cosmic microwave background that I showed you would have certain characteristic features. If we were to observe the opposite of these, so one possibility is an open universe with negative spatial curvature. Another one is a closed universe with positive spatial curvature. If we were to observe that our universe is closed, we would falsify this idea. This could not be the origin of the universe we live in. On the other hand, if we were to observe certain features in the cosmic microwave background, and I'll mention a few of those later, those would be very difficult to explain in any other way. So this theory makes predictions that if you observe the opposite would falsify it, and if you observe what it predicts would be strongly supportive of it, which is a characteristic that it's nice to have in a scientific theory. Some would say it's the definition of a scientific theory. So as I mentioned, many of the most basic characteristics of our universe can be explained by this picture. But when you dig more into this theory, you notice several facts which are somewhat disturbing. So one of them is that most of these bubble verses, so to speak, these universes inside bubbles are empty. They either recollapse in a tiny, tiny fraction of a second, or they expand so quickly that nothing interesting can happen. It's impossible to form stars or galaxies because any matter, any quantum fluctuation inside these universes is just torn apart by this rapid expansion. I mentioned that in Einstein's theory, the space between the galaxies grows, but the galaxies themselves don't because they're bound together. If the expansion is rapid enough, if the vacuum energy is large enough, then even if you somehow had a galaxy, it wouldn't survive. It would be torn apart by this expansion. So most of these bubbles are like that. But a tiny fraction of them happen to contain phases with very small vacuum energy. So let's focus on those because those are the interesting ones. Those look very similar to the universe we live in. When they first appear, they expand very rapidly and they grow to an enormous size. They're full of a hot plasma, which gradually cools. Quantum fluctuations inside these bubbles lay the seeds for structures that eventually form galaxies after billions of years. And around the time that those structures form, that tiny vacuum energy that I mentioned comes into play and starts to cause the expansion of the universe to accelerate again, which is something we've known is happening in our universe for about 20, 25 years now. So these features are, in fact, very much like the ones we observe in our universe. So this is more than just, there's a bit more of the same beyond our horizon when we talk about the multiverse. Because if this picture is true, then our observable universe is some part, probably a small part of one of these bubbles. That bubble is inside a parent state, just like a bubble of gas in a glass of champagne has a liquid champagne around it. So that bubble itself is surrounded by some parent vacuum. That parent vacuum contains other bubbles, some of which might be containing the same phase as the one that we're in, and others could have different phases. The parent vacuum itself could be a bubble that formed from its own grandparent phase. And we can speculate about this in much the same way that if we lived on that island I showed you before, and we discovered volcanism, maybe it's a volcanic island, and we have a theory of how volcanoes form. They form on the seabed and they erupt, and eventually you have an island. Then we might speculate that there should be other islands even though we can't see them or sail to them. Because if you have one volcano, why not another? So similarly, we might speculate that if we have one universe like the one we live in, one bubble like the one we're inside of, why not others? I mentioned before that these different phases vary not only in the vacuum energy, but even in the effective laws of physics. Not everything varies according to string theory. Some laws are universal, but particles, forces, and even numbers of space dimensions. It's possible for regions with different numbers of large space dimensions to fit together. That's a very interesting topic. All of these regions and these bubbles are expanding, but some more rapidly. And so the whole structure, this giant yeasty thing full of all of these bubbles, it grows and expands perpetually. So a question that often arises in discussing the multiverse is how scientific are these ideas? So I've already mentioned that living in one of these bubbles makes certain predictions. It predicts certain characteristic features, such as negative spatial curvature. And it can account for some of the features of our universe that otherwise would be very difficult to explain. But that's living inside one of these bubbles. It doesn't really test this bigger idea. So is there some way to test this whole multiverse structure? Is there something that we could do that would tell us about what's beyond our horizon? Because remember, our horizon is just a small region of one of these bubbles. So any other bubbles are beyond our horizon. How could we ever know that they're there or gather evidence for it? So if we come back to this island, you can't see beyond your horizon. You don't have any wood to build a boat, so you can't sail around. But you might one day, walking on the beach, come across something that doesn't belong there, like a plastic bottle or a branch of a tree that doesn't grow on your island, or a bird that's not native to your island. After all, the horizon is not a wall that prevents anything from coming to you. It's just it just limits what you can see from your own island. So it is possible to find signals that indicate that there's something more beyond, that there are other islands. In this cosmic multiverse full of these bubbles that I've been describing, inside this parent vacuum, this parent phase, these bubbles expand, and sometimes they bump into each other. They collide with each other. If you're inside one of these bubbles when it collides with another, you can ask the question, what would that look like? Is it something you could observe? So you can imagine, to have a picture in your head, two soap bubbles. One is full of smoke of one color and one of a different color. When they collide, there will be a wall that separates these two colors. And in the cosmology context I've been describing, if these two phases are different, so that's why I'm saying the smokes are different colors. If these two phases are different, one of them will have a different vacuum energy than the other, and that will exert a pressure on that domain wall that separates the two bubbles from each other, which will cause the wall to expand into one or the other bubble very, very rapidly. So that wall comes flying in at nearly the speed of light into one of these bubbles. And if a wall like that were to reach Earth, we'd be gone, because it would be very high energy density and moving at nearly the speed of light. The only good thing about it is that, first of all, it's unlikely to happen. And second of all, if it did hit us, we'd have no warning. It would go from our toes to our head in a much shorter time than it takes a nerve impulse to travel. So we'd have no idea it was coming. But it's unlikely to happen. And the reason is that nature prefers lower energies. Forces act to reduce energy or downhill to lower energy. And we live in a bubble with very, very low vacuum energy. So probably whatever bubble we collide with, the wall that's between us is not going to accelerate towards us, but rather away from us. Even if that happens, even if it accelerates away from us, the force of this collision still perturbs the universe we live in. It causes an enormous amount of energy to be injected into our bubble, into our universe. And that energy propagates across the plasma in the early universe, and it leaves a trace, it leaves an imprint on this cosmic microwave background. Maybe it's not surprising that it makes a circular or disc-shaped pattern on the sky. If you just imagine these two soap bubbles colliding, you'll get the picture. The domain wall between them would be round. And inside that pattern, inside that region, the temperature in the cosmic microwave background is affected. It can be colder or hotter with a certain characteristic pattern. So again, I'm not going to take the time to explain these predictions, but there are some specific predictions you can make for the temperature and the polarization of this cosmic microwave background. Observers have searched for that. They have found several anomalies in the CMB that are a rough match, but the match is not good enough to be statistically significant. And this could mean one of two things. Quite likely, it's not a match. It's not a signal of a cosmic bubble collision. It's just a coincidence that there's a spot on the cosmic microwave background which is hotter or colder than you would expect. But it could be that, in fact, it is a signal of a cosmic bubble collision, but the effect is too weak to rise above the noise and to reach what we call statistical significance, where we would take it very seriously. You might wonder why these signals are possibly visible if they are coming from outside, from beyond the horizon. But it's just like the driftwood. The reason that they're possibly visible is that they really came from before the Big Bang. They came from outside the universe itself, the universe that we live in, the bubble. And they propagate in, coming from really literally before the Big Bang, which was not the beginning of time here, because the Big Bang was the formation of the bubble. And that's why the cosmic horizon in this theory does not actually limit what we can observe. It limits what we can see directly, but not what we can observe with this sort of a signal. So lastly, I just wanted to comment, and then I'll finish, on what it might mean if we were to confirm in some way the existence of the multiverse, maybe through the ideas I've described here or some other ideas. So I think in the history of the human race, we started off believing that we were very special, created in the image of God, at the center of the universe with everything orbiting around us. And over time, over human history, that self-importance and centrality has eroded through a series of existential crises. So we went from thinking that the Earth was the center of everything to the Earth orbiting around the sun. And then we learned that the sun is unexceptional. There's nothing special about it. It's a quite ordinary star in a galaxy that contains actually hundreds of billions of stars. And then we learned that our galaxy is not particularly exceptional either. It's a relatively typical galaxy, and we can see hundreds of billions of others. And that's about all we can see directly, as we've described. But what's next? Could it be that the part of the galaxy we can see is just a tiny part of this much, much larger multiverse? So we don't know. That might be true. If string theory is correct, I think it probably is true. But we don't have direct evidence that string theory is correct any more than we have direct evidence that the multiverse is true. So we don't know for sure. But if these ideas hold, then our entire observable universe is a small part of one bubble, which is a tiny part of some probably infinite whole that contains a vast array of other universes. And all of the work that we've done over human history to discover the laws of physics and chemistry and biology, those laws are not fundamental. They're analogous to measuring the speed of sound, let's say in the air, and then noticing that the speed of sound in water is different. So you spend a lot of time measuring the speed of sound in air, and maybe you thought that was a truly fundamental fact about the world, but it's not. You change the temperature or the density of the air, or you go and measure sound in water and you measure the speed there, it's different. So string theory makes a prediction like that there are different phases with different effective laws of physics. We shouldn't believe this. I don't believe it necessarily. You shouldn't believe it either, because extraordinary claims require extraordinary evidence. So before we should come to believe something this radical, we should have very strong evidence, and we're not there yet. But maybe we'll get there eventually. So just to summarize what I said, and Maulik, you told me around 40 minutes, so I'll stop in just a minute. The multiverse is the idea that there's something beyond the immediately observable universe that we can see directly. Quantum mechanics and string theory together predict that our universe is contained in some very diverse, ever-growing multiverse. and that whatever lies beyond what we can see, at least far enough beyond, is not just more of the same, but really totally different or almost totally different than what's within. This is actually potentially observable if we're lucky, because our bubble has and will collide with other bubbles, and those collisions have effects that we could measure. And it's also falsifiable. There are observations we could make that would rule this theory out. So I'll stop there and just end with another image of our universe. So thank you.
Thank you for that, Matt. That was fascinating. We've have a lot of questions coming in the Q&A. Please also, actually, you can also enter them into the chat. I'm not sure which is better. Um, so let me start with some questions that we had earlier. Giovanni Catano is asking about that picture that you had of the CMB. There appear to be some areas, some sort of larger areas where it's blue, where it seems to be significantly bluer, and other areas where it's where there's a lot of red. You can see sort of it doesn't look entirely random. There seems to be some dark regions. Can you comment on those?
Yeah, so the human eye and the human brain are excellent at finding patterns. That's how we evolved. And so even when we look at a truly random field, we immediately focus on regions that look unusual. Um, I think though that if you took a truly random field, and of course people have done this in terms of doing simulations of the cosmic microwave background. So if you make a truly random pattern, and you know it's random because you've generated it with a computer simulation, it wouldn't look very different from this. You would see some regions that are, um, you know, that look anomalously cold or anomalously hot. So to really figure out if something is significant, that we should take it seriously as a departure from randomness, it has to be sufficiently different from what you would expect that the probability of it happening by chance is quite small. And so that's the analysis I was referring to when I said that there are anomalous features in this, but they're not significant enough to be taken very seriously, at least not yet.
Right. I think that there's even a place where Stephen Hawking's initials appear, right?
Yeah, it's somewhere in
Um, yeah. Um, so Paul Davies is asking, could you please elaborate on the self-reproducing aspect of the multiverse? And how does it contrast with, say, cosmological natural selection that Smolin has talked about?
Well, the self-reproducing aspect is that with positive vacuum energy, space expands, and that causes any phase with positive vacuum energy to grow exponentially, to double in volume every characteristic period of time, where that time depends on the vacuum energy. Since those phases are unstable, they can form bubbles of other phases. Uh, if you start with some parent phase, it will double in volume and then maybe double again, and then it will form a bubble of some other phase. But you still have some of the parent vacuum left over. And what's left over will double in volume and double again, and then form another bubble of some other phase. And there doesn't seem to be anything that stops this process. It's a version of so-called eternal inflation. So that's the basic idea. Uh, it just doesn't seem like there's an end to this. Um, any reason why there should be an end. And that applies even to the universe that we live in now. As far as we can tell, the vacuum energy of the universe we live in is small but positive, and it's causing the expansion to accelerate. Unless that energy decays or disappears in some way, uh, the part of the universe we live in will expand and grow forever. Um, so
So there are these infinite universes within other infinite universes.
yes, yes.
Yeah. So you mentioned that the parent universe can expand forever. Well, and anytime there's positive vacuum energy, you'll have essentially an eternal universe, a future eternal universe. But what about the past? Does the multiverse, the parent universe, have a beginning? That's a
It,
question from Howard Lannis.
it's a great question. Yeah, there's a theorem which under certain assumptions tells you that there cannot be an infinite past, that there must have been a singularity at some point in the past. So I explained how the Big Bang, which if Einstein's equations were exactly correct, would would have been a singularity about 14 billion years in our past. I explained how that might not be a singularity, but instead it could be the nucleation of one of these bubbles. But there's a more sophisticated theorem that with some assumptions predicts that even though that's true, if you go back far enough, not just in our bubble, but in the parent and the parent of the parent and so on, eventually there has to be a singularity in the past. But that theorem does rely on some assumptions, and it's not entirely clear that those are valid. So I would say we don't know. Probably there was a singularity in our past, but perhaps the universe could be infinite both in the past and towards the future.
So John Stanley asks, well, if nothing was there to measure the beginning of the universe during its singularity moment, how did it begin? Uh, Seems like we need to explain the singularity somehow or other.
Well, indeed, if there was a singularity in the past, you can certainly ask, what about that? Did anything come before? Was that the beginning of time? One of the things I found fascinating in Stephen Hawking's book when I read it as a kid was that he had ideas with real substance about that. So there are theories in physics, some of which Hawking has contributed to, where time really can begin. And one of them, the beginning of time is a bit like the South Pole. So going back in time, let's say, is going south, going forward in time is going north. And apologies to those of you in Australia, but so as you go south, you just end up at the South Pole, and there's nothing singular there. There's nothing special really about the South Pole. It's kind of a point that we just picked out and decided we would call that the South Pole. I mean, there's the rotation of the Earth, but that's irrelevant for what I'm saying. So in one of Hawking's theories, the beginning of time is like that. It's not really a singularity. It's smoother than that. And it's analogous to the South Pole. I don't know if that answers the question, but it's an interesting idea.
So here's another great question. This is from Ross Demott. Uh, does the background phase of the universe have 3 + 1 dimensions? That is 3 dimensions of space and 1 dimension of time, like our universe. Does it even make sense to talk about the dimensionality of the background? And that's
It make
particularly interesting because string theory has so many different dimensions.
Yeah, no, it makes sense. So in string theory, there are more than 3 + 1 dimensions. There's a version of the theory called M theory in which there are 10 spatial dimensions in one time. And this number may sound random and mysterious, and it is, but it comes out of the mathematics of the theory. It's the one answer in which the theory is mathematically consistent. So since obviously we don't see more than 3 dimensions of space around us, the first question you should ask is what happens to these other dimensions? And the answer in string theory is that they are compactified. So I mentioned that in Einstein's theory of general relativity, space is dynamical. It's not a rigid fixed structure. And one of the possibilities for space is that it wraps around on itself in certain directions. So in order to explain why we see 3 spatial dimensions around us, the rest of the spatial dimensions have to wrap around on themselves. And they have to do that in a sufficiently small distance that we wouldn't notice them. It's a bit hard to explain this. There are lots of great analogies that help, but essentially if some dimensions are compactified, it's called, and if the scale of that compactification is sufficiently small, you wouldn't be able to tell it was there. So the way the number of spatial dimensions can change in these different phases and in different parts of the multiverse is that a dimension that's compactified and very small in, let's say, our phase might not be compactified, or it might be much larger in a different phase. And so you can connect parts of the universe with different numbers of large dimensions. But in some sense, all parts of the universe have the same number of dimensions. They all have, let's say, 10 spatial dimensions. It's just that in some parts of the universe, 6 of those are compact, and in other parts, a different number might be compact.
Right. A question from Barbara Temple. Would proving or disproving the bubble universe provide a way then of making string theory falsifiable?
Well, it's hard to answer that honestly in saying absolutely yes, because we don't understand string theory very well still, even after all this time. It's a very, very difficult theory to work out the consequences of. An analogy actually is general relativity. When Einstein wrote down the theory in 1915, he really wrote it down in essentially the same form that we know it now. And yet it took decades and decades, really half a century, before many of its implications were understood. For example, the existence of black holes, or even the fact that the universe was expanding, those things, or the existence of gravitational waves, many of these things were not immediately obvious because the mathematics of general relativity is so hard that it took theoretical physicists and mathematicians a long time to understand. String theory is like that. It has a mathematical structure that's extremely difficult to analyze. So it's hard to say anything with true confidence about string theory. Um, I think at the very least, though, the observations I was describing would falsify this picture. They would falsify the idea that our universe is originated from one of these bubbles inside the multiverse.
Let's talk a little bit about bubble collisions, which is one of the things you worked on a lot. Um, so, first of all, I have a question. Is it automatically the case that if there's false vacuum decay, and we get hit by a domain wall that we're dead? Does it depend on the energy difference between the vacua? Is it possible that very, very a very small difference in vacuum energy could actually be harmless?
Um, well, I mean, I guess you could get hit by an aircraft carrier and be okay if it was moving extremely slowly, right? So if you somehow tune things so that the difference in vacuum energy is incredibly tiny, so that, or maybe it's even zero because there's some symmetry. So the wall is not moving or it's moving very slowly relative to the speed of light, then yes, I think it's at least in principle possible. But the scale of these things is such that um, even a very small fractional difference in vacuum energy corresponds to a very large acceleration of this wall, and therefore it will be moving at essentially the speed of light one way or the other. So it would require a really special coincidence for that to happen.
Mhm. Well, the fact that our own universe has such a low vacuum energy uh, means that any other positive vacuum energy would have to be even lower. And so that's just a
Yes,
very, yeah, so there's maybe a small chance that we could survive such a thing.
that's true. Yeah.
Um, so there's a question, I think, also from Giovanni Catano, who asks, should we not see lots of anomalies from potential collisions all over the sky?
Yeah, that's a great question. So the reason that we don't, if they're there, if they happen, the reason that we wouldn't is related to the rapid phase of initial expansion that I mentioned. So the phase of the universe that in the standard cosmological model, which doesn't include these bubbles or bubble collisions, but the phase of the universe during which these quantum fluctuations happen, the one that laid the seeds for galaxies, that phase is called cosmic inflation. So it's a very rapid, accelerated expansion that cosmologists believe happened in the early universe. And much like financial inflation wipes out your bank account if it goes on for long enough, cosmic inflation wipes out whatever was there to begin with. It does an excellent job of erasing traces of whatever was there before. Essentially, you expand so much that you dilute away anything that was there. So there could have been very many bubble collisions bubbles that ran into the universe we live in, um, but their traces would be very faint and perhaps undetectably so if there was enough cosmic inflation after our bubble appeared. So this is actually one reason why we may never know. Enough inflation will hide all of this from us and make it very difficult to detect, at least by this method. So we have to get a bit lucky and hope that inflation didn't last too long, and then we have a chance of seeing it.
Here's another question from Barbara Temple. Sometimes see, she writes, actual soap bubbles, where one has become attached to another,
Mhm.
uh, with a hemisphere of one bubble sticking out of the other one. Could two universes find themselves in a similar situation?
Yes, absolutely. Yeah, once they collide, they never come unstuck, or at least I don't think they can. Not in the theories that I've studied. They they both continue to expand, and the wall between them moves one way or the other, but they never detach. So these bubbles form clusters of bubbles, which you've probably also seen in subbubbles.
Okay, here's a question from Dave Bird asking about vacuum energy, which underlies all of this. Have we been able to make any progress in understanding why the vacuum energy calculated from quantum mechanics is so much larger than what has to be the vacuum energy that we observe? So this is the notorious cosmological constant problem.
Yeah, so this has been characterized as the most important and difficult question in fundamental physics. Um, have we made progress? I think that depends on your perspective. So in this picture, um, there is an explanation, which is that there are an enormous number of different phases, and each of these phases has a different value of the vacuum energy. And as far as we can tell, those values are distributed not randomly, but relatively uniformly across both negative and positive values. Both of them are possible. And so it's very likely that there are phases in which the vacuum energy just happens to be small. So you could imagine a dartboard and you want to be really close to the bullseye. That's the vacuum energy we measure. And then you throw a billion darts at your dartboard. Some of them are going to land very, very close to that point by coincidence. So that's the best explanation in this framework. It's not very satisfying. It would be much nicer if we had a calculation we could do that said, you know, the value of vacuum energy that we observe is the one that we can calculate. That's not the case here. But it does at least give you a way for there to be phases in which the vacuum energy is consistent with observation. And there's also the fact that if the vacuum energy would be significantly larger than what we observe, either positive or negative, then there'd be nothing of interest in those bubbles. I mentioned that briefly. If the vacuum energy is negative, they recollapse almost immediately. And if it's large and positive, they expand so rapidly that structures can't form. And so there's no one in those universes to wonder what the vacuum energy should be.
That's the infamous anthropic argument, which leads to a question by James Benford, who asks, could our universe, which seems so tuned, have been created by intelligent super civilizations in a previous universe, or is there another explanation? I think you were heading towards that explanation.
Well, I certainly think there are other explanations. Could it have been created by a super intelligent civilization? Sure. Why not? But it's hard to make scientific progress, I think, with that idea unless we come across really concrete evidence for it.
Yeah, but can you comment on why the non-super intelligent explanation for why the universe seems so tuned? Maybe
Yeah.
say a bit more
Well,
about
I
the
guess,
argument.
yeah. So the vacuum energy is perhaps the prototypical example of that. Um, and I gave some indications towards that explanation that if it were significantly larger by a factor of 10 or 100 even, then what we observe, then at least assuming that everything else would remain the same, but we would just experiment with the universe by increasing its vacuum energy, we would destroy almost all of the galaxies and stars and so on that actually exist. And if it were to become negative, it would cause the universe to recollapse before stars could light up and ignite. Um, so at least all else held fixed, which is a big assumption and one that you should certainly question. If you just vary the vacuum energy, it has to be in a reasonably narrow range around the value we observe to allow structures to form and at least be common in the universe. So that's a mild type of anthropic explanation. It says that if we were to change one thing, then the universe would be very, very different and we wouldn't be around to ask about it. It's not a particularly satisfying explanation in my view, but we don't really have a better one. In any case, that sort of explanation can be used for some of the other fine-tuning problems in our universe, although probably not for all.
Yeah, it's sort of like asking, if in a world where in a universe that couldn't produce atoms, there would be nobody to ask, why it
Why
looks so.
there are atoms, right?
Yeah. Um, okay, well, I think we're just about out of time. Thank you so much, Matt, for this wonderful talk and taking all these questions. And to everyone else, see you next month. Thanks
Thank you,
for,
Maulik. It's been my pleasure.
bye-bye.